Good afternoon, everyone. Welcome back to the third session of the third day of the FDP, that is 12th January. So we are again here with Dr. Praveen Kumar Mishra sir, and we are waiting for him to join. Abhinav sir, today sir is having some technical problem. He is not able to join via link.
Okay, ma'am.
Oh, he's dead now. He's dead. Welcome back, sir. Again, we are here on the third day of the third session of this FDP on data science with statistical methods using R programming. Sir, you are mute.
No, I'm unmute.
Not audible, sir.
Now audible?
No, not audible.
But
you are unmute, but your voice is not coming.
Oh.
Ma'am, sir is audible.
Sir is audible?
Yes, ma'am.
Hello.
Yes.
Okay.
Yes, sir. Your voice is coming, sir. You are audible, sir.
Okay. I think something wrong with the MAM system.
Technical problems, sir. We can't handle.
Yes. 2 days without any glitches, and now on third day something is going on. So how many participants are there? Only 35. Can we start?
Yes, sir. We can start.
Okay. So just a second.
What are we going to study now, sir?
Just a second, ma'am. I'm just sharing my PPT. Is it visible to all of you?
Yes, multivariate analysis and cases.
So in this session, we are going to discuss some multivariate techniques, multivariate analysis and principal component analysis. And if the time left, we'll discuss also factor analysis. It all depends on the time as well as my speaking ability, how much I can speak after 2 lectures. So it depends totally on that. So I'm going to start. I think I am visible as well as audible to all of you. Okay. So before starting the topic multivariate analysis, all of you are aware that the variables, when we study the variables, like in statistics, where we start with univariate statistics or one variable statistics. We take one variable like height of the students, marks of the students, or means single variable, age, uh, so many factors, and we study the distributions of that single variable. There are many distributions, like we start with the very basic Bernoulli distribution, and then we generalize it. If there are n experiments, the Bernoulli distributions for only 2 trials, and if we generalize it for n trials, then it will become a Bernoulli binomial distribution. Then for rare events, for univariate is Poisson distribution, and then we come to normal distribution. All the distributions under certain conditions tends to normality. So normal distribution is that distribution which include all the distributions under certain conditions, or for large values of n or large sample values, all the distribution tends to normality. So if the variables we have studied normal distribution for one variable, then bivariate normal distribution, and then the generalization or extension of that normal distribution is multivariate normal distribution, and that we study in multivariate analysis. So basic concept of multivariate analysis. Multivariate analysis is the analysis of observations on several variables, several correlated variables. This is one more important thing, that if the variables are independent, then multivariate there is means no use of studying multivariate analysis, because independent variables can be studied separately. So on several correlated variables, random variables for number of individuals in one or more samples simultaneously, this analysis has been used in almost all scientific studies. For example, the data may be the nutritional anthropometrical experiments like height, weight, arm circumstances, chest circumstances, etc., taken from randomly selected students to assess their nutritional studies. Since here we are considering more than one variable, so this is called multivariate analysis. The sample data may be the collection of measurements such as length, breadth of petal and sepal of different flowers from two different species to identify their group characteristics. The sample data may be collection of measurements such as length and breadth of petals and sepals of different flowers from two different species to identify their group characteristics. The data may be information such as annual income, saving, assets, and number of children, and so on, collected from randomly selected families. As in univariate case, we shall assume that a random sample of multivariate observations has been collected from an infinite or finite population. Also, the multivariate technique, like their univariate counterpart, allow one to evaluate hypotheses or results regarding the population by means of sample observations. So for this purpose, we consider the multiple measurements together as a system of measurements. Suppose this is xi alpha, we denote this measurement as xi alpha, denotes the ith measurement of alphath individual. Normally we denote the number of variables by small p and the number of individuals by small n. The n measurements on p variables can be arranged sorry, like this. On this side, vertical side, these are characteristics or variables x1, x2, xi, xp, and on this side, these are individuals 1, 2, alpha dash 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 n. So the first value here you can see first value is x11, Then the second value is x12 means the value of characteristic of second individual x12, x1 alpha, x1n, and so on. This is the representation. Now this can be written in the matrix form uh, like this x11 up to x1n, and this can be this earlier I have denoted here it was xi alpha. So this xi alpha is expressed in the matrix form like this, where the values of I are going from 1 to p and the values of alpha are going from 1 to n.
I request all the participants to please keep your mic on mute condition.
This is also known as data matrix. This xi alpha is known as data matrix. Now the main aim of the most of the multivariate techniques is to summarize a large body of data by means of relatively few parameters. Means you cannot draw any inference from this matrix itself. So you have to calculate some parameters for this data, and normally those parameters are mean, variance, correlation coefficient, etc. So, or to reduce the number of variables by employing some techniques, multivariate techniques. Again, this suitable linear transformations and choose a very limited number of the resulting linear combination in some optimum manner. Disregarding the remaining linear combination in the hope that they do not contain much information. Among the multiple techniques, there are two main groups. Such methods concerned with the relationship between variables called variable oriented, and the important variable oriented techniques are total, partial, multiple, and canonical correlations, principal component analysis, and so on. While the other group concerned with the relationship between individuals and called individual oriented, in such cases, problem of classification arises to assign an individual of unknown origin. One of the two populations we may make discriminant analysis. This classification problem we have already studied, right? There are so many classification techniques. So before going to multivariate analysis, it is very important to know some basic mathematical techniques, basic mathematical tools, and one of which very important tool is matrix theory. So basic theory of matrices is very much required for the study of this multivariate analysis. So suppose given a P cross P matrix, square matrix, suppose it is denoted by capital A, and we can denote its components like Aij, the elements A11 up to APP from the principal diagonal, or simply the diagonal of A. We are aware of this and are called its diagonal elements, whereas the elements A1P, A2P minus 1, AP1 constitute the secondary diagonal of A. For I not equal to j, Aij are the diagonal elements of A. Now the matrix of order P, say Aij, is said to be symmetric. It will be symmetric if Aij equal to Aj for all I, j values 1 to p, or we can write it like A is equal to A dash. Skew symmetric matrix if Aij is equal to minus times Aj for all I, j, then we say that it is skew symmetric and A is equal to minus times A dash. A matrix capital A is equal to Aij is called diagonal matrix if Aij equal to 0 for all I not equal to j, and we can write A is equal to diagonal of A11, A12 and so on APP. Sorry. A non-zero diagonal matrix whose diagonal elements are all equal is called scalar matrix, and a scalar matrix whose diagonal elements are all unity is called a unit matrix or an identity matrix. A matrix is generally denoted by capital I, in which case a scalar matrix is of the form Ci, where C is some non-zero scalar. It may be easily seen that AI equal to A. IB equal to B, A of Ci is equal to CA, AIB is equal to AB, provided that products are all defined. A square matrix A is equal to Aij is said to be upper triangular if Aij is equal to 0 for all I less than j. Means upper triangular means or lower triangular elements are 0. And it is called lower triangular if Aij is equal to 0 for I less than j. If A is either upper or lower triangular. A square matrix capital A is said to be idempotent if A square equal to A, means if we square the matrix and we get the same matrix, then it is said to be square matrix. A square matrix capital A is said to be orthogonal if we take the matrix and multiply it by its transpose, and if we take the transpose and we multiply it by the matrix, we will get the identity matrix, then it is said to be orthogonal. Let AI dash denote the ith row of matrix A is equal to Aij of order P, and Bj its jth column, then ijth element of AA dash and A dash A are AI dash and Aj and Bi dash Bj respectively. Now if A is orthogonal, that means AA dash equal to A dash A, then A dash Aj and both will be equal to 1 if I equal to j and equal to 0 whenever I not equal to j. Thus both A1, A2 up to AP and B1, B2, BP are orthonormal. Now the next definition is the trace of a matrix A. Trace of matrix A, it is denoted by A. TR, we write it like TR of A, is the sum of diagonal elements of A, which is the sum all diagonal elements. Trace of A plus B will be equal to trace of A and trace of B whenever A and B are square matrices of same order. Trace of AB will be, it follow this rule, trace of AB will be equivalent to trace of BA whenever both AB and BA are defined. Similarly, trace of ABC equal to trace of BCA equal to trace of CAB, provided all the three products are defined. A square matrix A is said to be non-singular if there exists a square matrix B of the same order called inverse of A such that AB equal to BA. That means inverse of A A is the matrix, non-singular matrix, and its inverse is A inverse, then AB is equal to BA equal to identity. If inverse of non-singular matrix is unique, and it is because of this uniqueness that the inverse of A, if it exists, generally denoted by A inverse. Now the inverse of inverse will be the same matrix. Transpose of inverse matrix will be the inverse of its transpose, where A is non-singular. Now AB, if AB is the product and we take its inverse, it will be equal to B inverse, A inverse, whenever A and B are non-singular matrices of same order. The determinant of a diagonal or triangular matrix equal to the product of its diagonal. Determinant of transpose equal to the determinant of the matrix. If we take determinant of AB, it will be equal to BA, and it will be the product of individual determinants as well. Determinant of A is not 0 if a non-singular matrix, since I is equal to A inverse, and so these are some properties which we should know. Some more mathematical results are here. A determinant of A, whenever A has 0 row or 0 column or two identical rows columns, the determinant changes sign if any two rows are interchanged. The determinant remains unaltered when row is replaced with sum of that row column and scalar multiple of another row. If A is diagonal of A11 up to AQQ, where A11, AQQ are the square matrix, then determinant of A will be equal to determinant of their separate product. Now, these are some important properties which are very much required for studying the multivariate analysis. Suppose given a matrix A of order P, the matrix A minus lambda I, where lambda is a scalar variable, is called the latent or characteristic matrix of A, and polynomial determinant A minus lambda I, which is of degree P, is called latent or characteristic polynomial of A, and the equation A minus lambda I is called characteristic equation. Now, if we write A minus lambda I as A0, A plus lambda 1 like this polynomial, it can be easily seen that A naught will be determinant A multiplied by this. Every square matrix satisfies its own characteristic equation. This is very important property. Given a square matrix A, the roots of characteristic equation are called its latent or characteristic roots or eigenvalues. So clearly, if A is P cross P, then A has small p latent roots. The latent roots of a diagonal or triangular matrix are their diagonal elements. The determinants of a square matrix is the product of its latent roots. The square matrix is non-singular if and only if none of its latent roots is 0. So there are so many properties which are very useful. It will be shared with you so that a number of properties are here. So now come to the point directly. The normal distribution, this is the density function of multivariate normal distribution. Suppose a random vector is x and its components are x1, x2 up to xp. So taking the sample values x1, x2, xp in Euclidean space of dimension p, it will said to have p-variate normal distribution if its probability density function can be written like this: fx equal to 1 upon 2 pi p by 2 sigma x. Now this sigma x is known as variance covariance matrix. This 1 by 2, this mu is the mean vector of multivariate normal distribution, where mu has the component mu1, mu2, and so on, mu p, and sigma is positive definite symmetric matrix of order p. It is known as variance covariance matrix of the multivariate normal distribution. Now come to the topic directly: dimensionality reduction. Increasing the number of features will not always improve classification accuracy. Dimensional. Now, what do you mean by dimensionality reduction? Dimensionality reduction means in any phenomena, the total variation of in any phenomena, the total variation has so many components. So many components. Suppose the variation, suppose it is 100. So there can be 35 components due to that 100 variation is coming. And out of all those 35 components, maybe there are only 4 components which are contributing the 95% variation, and rest 31 components are contributing only 1% variation. So the aim here is means dimensionality reduction. So aim is to find out, to find out those 4 components who are contributing the variation maximum. Due to those components, maximum variation is there. So how to find those 4 components out of these 35 components? This is called dimensionality reduction. But it is not means once you see 35, there are 35 components. So it is not written on the face of each component that I am contributing this much of variation. So it is our job to find which component is contributing maximum variance. But sometimes it happens that we eliminate some components, and or we pool some components, and they are contributing less, but they are important. So increasing the number of features will not always improve the classification accuracy. In practice, the inclusion of more features might actually lead to worse performance. It may happen. Increasing the number of features. In practice, inclusion of the number of training examples required increases exponentially with dimensionality. So D, it increases number of wins per feature. Here you can see 3 raised power 1 bins, k is equal to 3, 3 power 2, 3 power 3. So what is the objective? Choose an optimum set of features of lower dimensionality to improve the classification accuracy. Here is the performance and here is the dimensionality. Different methods can be used to reduce dimensionality. First is feature extraction, feature selection. Feature extraction finds a set of new features, that is, sorry, I have to receive a call.
सरांनी घेतली बरं सर तुम्ही चेअर तिथे चेअरवर बसा
So feature extraction finds a set of new features, that is through some mapping from existing features like x, x1, x2, xn. If function of x, it is a function mapping, or y equal to y1, y2, yk. The mapping F could be linear or non-linear, both type of mapping. So feature selection chooses a subset of the original features like x, x1, x2, xn, and y equal to xi1, xi2. Again, it will be breaked into components. Linear combinations are particularly attractive because they are simpler to compute and analytically tractable. Given x belongs to Rn, find an k cross n matrix T such that y equal to Tx belongs to Rk, where k is less than or equal to n. Here is the transformation, which can be this is a projection from n-dimensional space to a k-dimensional space. From a mathematical point of view, finding an optimum mapping y equal to fx is equivalent to optimizing an objective criteria. Different methods use different objective criteria. For example, minimize information loss. It represents the data as accurately as possible in the lower dimensional space. Then maximize discriminatory information. It enhances the class discriminatory information in the lower dimensional space. Then popular linear feature extraction methods are first is principal component analysis, that is PCA, seeks a projection that preserves as much information in the data as possible. Then there is linear discriminant analysis, LDA. It seeks a projection that best discriminates the data. Many other methods are like making features as independent as possible, independent component analysis, ICA, then retaining interesting directions, projection pursuit, embedding to lower dimensional manifolds, isomap, locally linear embedding, LLE. Then vector representation. A vector X belongs to Rn can be represented by n components like this: x equal to x1, x2, xn. Assuming the standard base v1, v2, vn, that is unit vectors in each dimension, xi can be obtained by projecting x along the direction of vi. Like xi is equal to this is the mathematical transformation. X can be reconstructed from its projections as follows: x equal to, this will be the linear combination, x equal to summation I is equal to 1 to n, xi vi, x1 v1, x2 v2, and so on, xn vn. Since the basis vectors are the same for all x belongs to Rn standard basis, we typically represent them as a n component vector like this. For assuming n equal to 2, so n x1 x2 equal to 3, 4, so this will be the coordinate. Assuming the standard base v1 equal to I, v2 equal to j, xi can be obtained by projecting x along the direction of vi, like this. X1 will be xti 3, 4, and it will be after multiplication we will get 3. X2 after multiplication 3, 4, 0, 1, so it will be 4. X can be reconstructed from its projections as follows: x equal to 3i plus 4j. So now come to the point, principal component analysis. If x belongs to Rn, then it can be written a linear combination of an orthonormal set of n basis vectors v1, v2 up to vn in Rn using the standard base vi, vj. Its value will be 1 if I equal to j, and its value will be 0 otherwise. So x, this will be the linear combination, x equal to summation of xi vi, x1 v1, x2 v2, xn vn, where xi is given by this, the components x1, x2 up to xn. PCA seeks to approximate small x in a subspace of Rn using new set of k less than or equal to n basis vectors u1, u2 up to uk in Rn is
Excuse
denoted
me.
by z.
Hello.
Yes,
Sir, you told that there are two ways of mapping, linear and non-linear.
yes.
What is the difference? What is the basic difference between the two? Hello.
Hello, hello.
Audible, sir.
Yes, sir.
Okay, okay, okay. Somebody was asking something.
Yes, sir. I was asking about what is the
Uh,
difference
le-
between
uh,
linear and non-linear.
linear and non-linear mappings, ma'am. The functions or equations which are mapping means some linear functions or linear line, right? And non-linear means those are mapping for curves. Some curves are there. The
Okay, okay.
basic basic difference is that. Actually, my
Okay,
connection
correct.
is not stable today. I don't know why. So I am struggling with that.
Okay, no issues, sir. Okay.
Sir, you are not audible.
Just a minute, ma'am. Just a minute.
Okay, fine.
Actually, my slide was also closed, so I'm just. So here we are. If X, am I audible?
Yes, sir.
Okay. Can be linear x belongs to R, and then can be written a linear combination of X and orthonormal set of n basis vector like this. So PCA seeks to approximate X or in subspace of Rn using a new set of k less than n basis like this. Such that the norm of x minus x hat is minimized. Minimized information is the optimal set of basis vectors u1, u2, uk can be found as follows. We'll see why. Find the eigenvectors ui of the covariance matrix of training data set sigma x, and sigma x ui is equal to lambda I ui. Then choose the k largest eigenvectors ui, that is corresponding to the k largest eigenvalues lambda, like this u1, u2, uk correspond to optimal basis. We refer to the largest eigenvectors ui as principal components. Suppose we are given x1, x2 up to xm n cross 1 vectors n of features m of data. Then step 1 is compute the sample mean by x bar equal to 1 upon m summation I going from 1 to m xi. Subtract the sample mean, that is the center data at 0, that is phi equal to xi minus x bar. Then step 3 is compute the sample covariance matrix sigma x. Sigma x will be 1 upon m. This it can be computed with this formula 1 upon m summation I 1 to m xi minus x bar transpose, and it will be equal to 1 upon m. This is phi here, so it will be phi I transpose. It will be equal to 1 upon m a transpose, where a is what? Phi 1, phi 2, dash 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 phi m, that is the columns of a are in phi I. N cross m matrix it will be. Compute the eigenvalues or eigenvectors of sigma x like this.
Sir, you are not audible.
Hello. Hello.
Audible, sir, audible.
Okay. So compute the eigenvalues oblique eigenvectors of sigma x like sigma x ui equal to lambda I ui. Where we assume that lambda 1 is greater than lambda 2 greater than lambda n. That means lambda 1 is the highest contributing variance component, lambda 2 is from that, and so on. Most software packages return the eigenvalues and corresponding eigenvectors in decreasing order. If not, you can explicitly put them in that order. Since sigma x is symmetric matrix, so u1, u2, un form an orthogonal basis in Rn, and we can represent any x belongs to Rn as x minus x bar will be equal to summation yi ui. It will be equivalent to y1 u1, y2 u2, and yn un. And yi will be equivalent to this value x minus x bar transpose ui upon ui transpose. So it can be written as x minus x bar transpose ui, where if ui is equal to 1. That is, this is just a change of basis only. X minus x bar can be represented like this: x1, x2 up to xn. It will be mapping y1, y2 up to y. Most software packages normalize UI to unit length to simplify calculations. If not, you can explicitly normalize them. Step 5, dimensionality reduction step. Approximate x using only the first k eigen vectors k less than n, that is corresponding to the k largest eigenvalues, where k is a parameter. X minus x bar will be equal to I going from 1 to n yi ui. It will be like this. Approximate x by x hat using first k eigenvectors only. That means x hat minus x bar will be equal to I going from 1 to k yi ui, y1 u1, y2 u2, and yk uk. So it will be like this. That if k is equal to n, then x hat equal to x bar. That is zero reconstruction error.
Sir, you are not audible.
Abhinav sir, is sir there in the meeting?
No, ma'am.
Send him invite. There is some problem at his end, I think. Please. Two
Am
people
I
are appearing unmuted, Rishikesh and Indu Yadav.
audible now?
Yes, you are
Yes, sir.
audible, sir.
Okay, okay.
Abhinav, please mute these Rishikesh and Indu Yadav.
Okay, ma'am.
You are visible and audible too, sir.
I don't know why it is happening again and again.
There might be some process, sir, which is not allowing your teams to respond. You will have to end all the tasks. You take this session and then you can have a look at it. Yes, the screen is visible, sir.
It is in slideshow mode?
No.
No. Oh. Now? Now?
Yes, sir. Now it is in slideshow. Yes, sir.
It's perfect, sir. You please start.
Okay. So the linear transformation y is equal to tx, which performs the dimensionality reduction in PCA is x hat minus x bar equal to I is equal to 1 to k yi ui, where y1 u1 plus y2 is the linear combination. X minus x hat minus x bar equal to u times y1 y2, where u is u1 u2 uk, and cross k matrix, that is the column of u are the first k eigenvectors of sigma x. So y1 y2 yk will be u trans x hat minus x bar. T is equal to ut k cross n matrix, that is the rows of T are the first k eigenvectors of sigma x. So what is the form of sigma y? Sigma x is what? 1 upon m, I going from 1 to m, xi minus x bar transpose. So it will be 1 upon capital M, I going from 1 to m, xi minus x by phi I minus phi I transpose. Using diagonalization, it will be sigma x equal to p AP transpose. The column of P are the eigenvectors of sigma x. The diagonal elements of lambda are the eigenvectors of sigma x or the variances. So yi is equal to ut xi minus x bar pt phi I, and sigma y will be 1 upon m, I going from 1 to m, yi minus y bar transpose. It will be 1 upon m, I going from 1 to m, yi minus yi transpose, and it will be equivalent to pt phi I whole transpose. These are the mathematical calculations, pt sigma xp. So the form of sigma y will be Wilks lambda. It's called Wilks lambda. So PCA decorrelates the data and preserves original variances. Now the interpretation of PCA chooses the Eigen Vectors of the covariance matrix corresponds to the largest eigenvalues. The eigenvalues correspond to the variance of the data along the eigenvector directions. Therefore, PCA projects the data along the directions where the data varies most. PCA preserves as much information in the data by preserving as much variance in the data. So U1 is the direction of maximum variation. Here you see U1 is the direction of maximum variation. U2 is orthogonal to U1. U2 is orthogonal to U1. Now compute the PCA principal component analysis for the following data set. Compute the sample covariance matrix like sigma hat equal to 1 upon n xk mu hat xk mu hat transport. So this is the variance covariance matrix for this data set. The eigenvalues can be computed by finding the roots of the characteristic for polynomial. Characteristic polynomial will be mx. So you see here from diagonal elements lambda is subtracted and determinant sigma x minus lambda I is calculated. So the value of lambda 1 means the first characteristic root is 9 and the value of lambda 2 is means the second latent root is 0.41. The eigen vectors are the solutions of the system summation x ui equal to lambda I ui. So we can write it like this with new 1 1 new 1 2. So lambda 1 new 1 1 lambda 1 new 2 2 is equal to this value, and these will be the values. So ui is the solution, and then cui is also the solution if c not equal to 0. Eigenvectors can be normalized to unit length using nu I cap equal to nu I of divided by norm of nu I. K is typically chosen based on how much information variance we want to preserve. Choose the smallest k that satisfy the following inequality. This inequality should be satisfied. The threshold where t is a threshold of 0.9. If t is equal to 0.9, for example, we preserve 90% of the information in the data. If k is equal to n, then we preserve 100% of the information in the data. Just a change of basis x hat equal to x. Approximation error. The approximation error or reconstruction error can be computed with norm of x minus x hat, where x hat will be summation I going from 1 to k yi ui plus x bar equal to y1 u1 plus y2 u2 up to yk uk plus x bar. It can also be shown that approximation error can be computed as follows. Norm of x minus x hat equal to 1 upon 2 I going from 1 k plus 1 to k lambda I. Data normalization. The principal components are dependent on the units used to measure the original variables as well as on the range of values they assume. The principal components are dependent on units used to measure the original variables as well as the range of values. Data should always be normalized prior to using PCA. A common normalization method is to transform all the data to have zero mean and unit standard deviation. That means it will follow normal distribution with mean 0 and variance 1. Standard deviation 1. That is xi minus mu upon sigma, where mu and sigma are the mean and standard deviations of ith feature. Applications to images. The goal is to represent images in a space of lower dimensionality using PCA, useful for various applications like face recognition, image compression, etc. Suppose there are m images of n cross n. So first represent each image as a one-dimensional vector by stacking the rows together. Note that face recognition faces must be centered and of same size, like this. The key challenge is that the covariance matrix sigma is now very large, n square multiplied by n square. So step 3, compute the covariance matrix sigma x. Sigma x will be computed like this, where A is phi 1, phi 2, phi m is n square cross m matrix. Sigma x is now an n square matrix, computationally expensive to compute its eigenvalues, eigenvectors. We will use a simple trick to get around this by relating the eigenvalues and eigenvectors of A transpose to A transpose A. Let us consider the matrix A transpose A instead of M cross M matrix. Suppose its eigenvalues oblique eigenvectors are mu I and nu I. Multiply both sides with A and we'll get A transpose A nu I is equal to mu I A nu I. Assuming A transpose mu I lambda I mu I, so we get lambda is equal to mu I and mu I is equal to A nu I, where A is this matrix. But do A transpose and A transpose A have the same number of eigenvalues, eigenvectors? A transpose can have up to n square eigenvalues, eigenvectors. A transpose A can have m eigenvalues and eigenvectors. It can be shown that m eigenvalues, eigenvectors of A transpose A are also the m largest eigenvalues, eigenvectors of A transpose. So PCA need to be updated as follows. Compute A transpose A instead of A transpose and compute mu I A transpose A. Then compute lambda I mu I of A transpose using lambda I is equal to mu I and mu I is equal to A mu I. Then normalize ui to unit length. Dimensionality reduction step approximate x using only the first k eigenvalues and eigenvectors. Each image can be represented by k-dimensional vector.
Sir, you are not audible. Sir.
Ma'am, sir is not online.
Sir is not in the meeting, na Abhinav?
No, ma'am.
I have heard.
Hello, madam.
Ji, sir.
Actually, he should have made some alternative arrangement. Pabin sir.
Sir, your voice is not coming clearly. What are you saying?
The research person should have made some alternative arrangements. If at all that in the laptop.
No, maybe there is some technical problem at his end, sir. It can be at anyone's end, no? Means he has already taken 4 sessions.
Ready
There
for
were
that.
no problems.
Okay.
Yes, sir, you are back.
I'm very sorry why I don't know why it is happening in this session. All other sessions were gone very smoothly. Maybe something is wrong with my laptop or something is wrong with network.
It often happens, sir. Don't worry. It can happen with anyone.
Is it visible?
Yes, but it is not in slideshow mode, sir.
Okay. Now it is visible to all of you?
Yes, sir, it's perfect.
Okay. So phase recognition using eigenfaces given an unknown phase x, follow these steps. Subtract mean x bar computed from training data, phi is equal to x minus x bar. Project unknown phase in eigenspace, phi equal to summation I going from 1 to k yi ui, where yi equal to phi transpose ui, where the space omega is y1 y2 up to yk. Find the closest match sigma I from training data set using ER minimum of omega minus omega I, that is minimum of summation yi minus yj I whole square, or minimum of this Mahalanobis distance. This is Euclidean distance. The distance ER is called distance in phase space. Recognize x as person k, where k is the ID linked to space. For intruder rejection, we need ER less than TR for some threshold TR. Now face detection versus recognition. This is detection, recognition, that is she is Sally. Given an unknown image X, subtract mean X bar computed from training data, phi is equal to X minus X bar. Project unknown phase in the eigenspace, phi is equal to summation yi ui, where yi is equal to phi transpose ui. Compute the value ed for norm of phi minus phi cap. The distance ed is called distance from phase space. If ed is less than td, then x is a phase. Then these are the inputs and reconstructed images. Reconstructed images looks like a face. Reconstructed image looks like a face. Can be used for face detection, tracking, and recognition. Limitations: background changes cause problems. De-emphasize the outside of the face by multiplying the input image by 2D Gaussian window centered on the face. Light changes degrade performance. Light normalizations might help, but this is a challenging issue. Performance decreases quickly with changes to face size. Scale input image to multiple sizes. Multi-scale eigenspaces. Performance decreases with the changes to face orientation, but not as fast as with scale changes. Out of plane rotations are more difficult to handle. Multi-orientation eigenspaces. PC is not always an optimal dimensionality reduction technique for classification purpose. Now, linear discriminant analysis. What is goal of linear discriminant analysis? It seeks to find directions along which the classes are best separated. That is, increase discriminatory information. It takes into consideration the scatter within the class and between the classes. So you can see bad separability, projection direction, and good separability. So let us assume C classes with each class containing mi samples, I going from 1 to C, and m is the total number of samples. The value of m is I going from 1 to C, mi. Let mu I is the mean of ith class. The values of I are varying from 1 to C, and mu is the mean of whole data set. So mu equal to 1 upon C, I going from 1 to C, mu I. Within class, scatter matrix SW will be I going from 1 to C, J going from 1 to Mi, X1J minus mu I, X1J minus mu I transpose. Between class scatter matrix is SB equal to I going from 1 to C. This will be the between class scatter matrix. Suppose the desired projection transformation is Y equal to UTX. Suppose the scatter matrices of projected data Y are SP hat and SW. LDA seeks transformations that maximizes the between class scatter and minimizes within class scatter. So maximum of SV upon this or maximum of this transformation. It can be shown that the columns of matrix U are the eigenvectors, that is called Fisher's spaces, corresponding to the largest eigenvalues of the following generalized eigenproblems. It can be shown that SB has the most rank C-1, therefore the maximum number of eigenvectors with non-zero eigenvalues is C-1. That is, maximum dimensionality of LDA subspace is C-1. When C is equal to 2, we always end up with one linear discriminant analysis feature, no matter what is the original number of feature was. If SW is non-singular, we can solve a conventional eigenvalue problem as follows. In practice, SW is singular due to high dimensionality of data and much lower number of data. To elevate this problem, PCA could be applied first. First, apply principal component analysis to reduce the data dimensionality like this. Then apply LDA to find the most discriminative directions. Now the last topic is vector analysis. Assume set of unobservable latent variables. Goal, characterize dependency among the observable using latent variables. Suppose group of variables having large correlation among themselves and a small correlation with other variables. Single factor. Assume k input factors latent or unobservable variable generating d observables. Assume all variations in observable variables are due to latent or noise with known variance. Find transformation from unobservable to observable which explain the data. Find a small number of factors z which when combined generate x minus mu I like this. This is the where zj, j equal to 1 to up to k are the latent factors with expectation of zj equal to 0 and variance of zj is equal to 1. Covariance of zj will be 0, I not equal to j. Epsilon I are the noise sources or random errors. Expectation of epsilon I is psi and covariance of epsilon I epsilon j equal to 0 where I not equal to j. And Vij are the factors loading. Find V such that S equal to V transpose plus psi, where S is the estimation of covariance matrix and V loading explanation by latent variables. V is D cross K matrix, K less than D, solutions using eigenvalues and eigenvectors. If factor analysis, in factor analysis, Zj are the stretched, rotated and translated to generate X. What are the usage? Speech is a function of position of a small number of articulators, lungs, lips, and tongue. Factor analysis go from signal space 4000 points to 500 ms to articulation space 20 points. Classify speech by 20 points. Speech compression send 20 values. I am very sorry that my network is not cooperating with me. Am I audible?
Yeah, sir, you're audible.
Okay, so my network is not means cooperating with me right now. So whatever the content I have speedily delivered, and I'm feeling extremely sorry for that. I will share the material with all of you, and I am concluding here only because it is happening again and again, and it looks very bad that means I am not able to deliver it properly. Why it is happening, I don't know, because it was gone very smoothly for last 3 lectures, but I think 4 lectures, but it is happening now. So I am very sorry, and I am concluding here. Anuradha ma'am.
Just 1 minute, sir.
Okay.
Yes, sir. Actually, we are also having simultaneous classes, so
Yeah,
managing
that is very difficult, but I don't know why it is happening again and again. And I covered very speedily the topics which I want to explain properly, but means I'm feeling very sorry that it.
No, sometimes it happens, sir. Don't feel sorry. You have given us so much time. Thank you so much for that.
No, means I'm feeling very extremely sorry because all the participants are sitting means after leaving all the work, and if means I'm not able to deliver properly, so it's not looks very good. But my connection is again and again disconnecting, so I don't know why it is happening. I am extremely sorry to all of you, but yeah, this happens. This is technology. And if it is a classroom teaching, means there are no glitches. I can continue for 2-3 hours. But right now it is means this network is not behaving properly, and I will screw up this network, and I will punish this network issues, address the issues.
Actually, sir, this FDP was approved in offline mode only, but keeping in mind the current COVID situation, I have converted it to offline mode. Sorry, to online mode. It was approved in offline by AICTE, but I thought I would not be able to manage offline things because of the COVID situation. So I had to convert it to online mode.
No, means sometimes it happens that I can continue with mobile also, but it will not be possible to explain these mathematical things with mobile phone. So it is very difficult, and sometimes you arrange everything, but it happens that nothing works. So in this lecture, it is happening means in that way. So I am
Any
means.
questions from anyone? Is if there is any doubt, then we can ask sir. Or sir can means I'm writing sir's mail ID in the chat box. If someone has problems, want to discuss, you can write to sir as well. You are mute, sir.
Ma'am, just post it in WhatsApp group, please.
Hello, am I
In the
audible?
WhatsApp group, right?
Am I audible?
Yes.
Please post my mail ID to all of the participants, so that we can contact, and if they have any query, so they can post.
Okay, if there is any doubt. Someone is writing also during online mode, many workshops faces the connectivity issues. This is Shekhar Gantyat, sir. So either it can be using mobile or Wi-Fi networks. He has also faced so many problems many times. Yes, sir, we can understand. Even when we are taking online classes, it was very difficult. The past 2 years during this pandemic were very difficult, taking classes in online mode, and technical glitches are there. Students also can't afford mobile data. They are having 7 to 8 classes back to back. So means I myself faced this, that my classes of one subject were scheduled at the last lecture 4:15. So one student was there, she never used to be able to join my classes, and we can't punish them in such cases. So this technical things have bound us all, but the better part is that 200 people are sitting in this class, which is not possible in offline mode.
So that is why, ma'am, I am feeling extremely sorry, because all of them are academicians, industry means from industry, and they are sparing their time to for this workshop. and it
Sir,
is
but your
only
content
for last lecture.
delivered it well also.
It is only for last lecture. I know that, but it should be perfect. From the next time, I will take care that it should not happen, even if it is not in my hands. Network is not in my hands, but I will try.
Sir,
It's okay, sir. We are fine. I mean,
I can share you my WhatsApp screen, sir. Everyone is writing that you have taken a very good lecture and this technology can overcome us. We can't help it. So don't feel so sorry.
Thank you so much for having so much of patience, all the participants. But actually, it was not in my hands, so that is why it happened. Thank you so much.
Okay, if there is any question, then you can ask, please. The session was nice. People are writing. Means Seema Yadav madam has written that it was a nice session. Okay, sir has again left. I will share the WhatsApp messages with sir. So I think we should end up. No, sir has again joined.
No, I don't know why it is happening. Again, my mic is mute and camera is off. I don't know what is going on. I am just sitting in front of the laptop and what is going on, I don't know. Maybe it is a network problem. Maybe my laptop is misbehaving because camera is creating the problem from the
Sir,
first
maybe
lecture.
your Teams is misbehaving. Maybe you will require to uninstall Teams and
Yeah,
install
yeah.
again.
Because
Maybe
other platforms are not misbehaving. Like I am using Zoom and Google Meet, they are working very properly.
actually
So
Teams is a very big software. It needs a lot of bandwidth to run.
okay.
That's why. But
Thank you so
I
much.
am also bound because our university's head office is at Noida. So if I go through Zoom or WebEx, it will take 10 days to 15 days for me to get the recorded sessions from Noida.
Oh my God.
That is why I can't afford that much of time gap. So that is why I have decided to take the sessions on Team because Teams is under our control. Whereas
Okay.
Zoom and WebEx, we have accessibility to everything, but the recorded sessions we will not get. We will get
Yeah.
in 10 days time or 15 days time.
Okay.
So this is why we have to take sessions on Teams. Okay, sir, people are asking for your presentations. Please do share. I will share with everyone.
Okay. I will share just after just leaving the meeting.
Yeah, okay. So can we end up the session? Girish sir is unmuted. Do you want to ask something, Girish sir? Sir is left. Okay, then we'll end up the session here. Thank you so much everyone for joining. We'll meet at 9:30 a.m. tomorrow.